So welcome to part 3 of lecture 35. Kind of in this part here, I'm just going to sketch out the basic idea behind the proof of the polar decomposition theorem. It's a fairly complicated proof and you can wade through all the details in the textbook, but I just wanted to kind of give you the big picture of kind of how it worked. Okay, and the reason that we want the polar decomposition is because we need this result in the last lecture, which will lecture 36. Okay, so let's just go over here. And I really do want to emphasize here that we're just sketching out the proof. Okay, now T is an operator, and so is this guy right here, okay, because you're taking the T composed with its adjoint. It's a positive operator, so it has a unique square root. That's also an operator, so they both live inside of this space. And more importantly, is that the range of this operator is a subspace of V, and the range of T is also a subspace of V. Okay, so you want to think about, I have my vector space V, and over here is all the things that are in the range of this operator. It's a subspace. I'm sorry, you can't see that very well. Let me try cleaning that up. Okay, so this is the first subspace, and then over here we have the second subspace, right? So this is the range of T. So both of these are subspaces of V. And the first part of the proof is to define a map from the red square to the red triangle, right? We're going to define a map from this subspace to this subspace. And the way that we define this map is we take something in here. So something in here looks like T star T evaluated at V, and we map it over to TV. Right, so if you have to remember that originally you had the vector space V, and it maps into side of here, right? So I can maybe draw that picture right here. So this would be my vector space V, and you have one map, right, that takes a vector V and maps it into side of this red box, or you have the other map which takes a vector and maps it inside of this red triangle. And what way we're going to define this map is say, okay, I take something over here, it had to come something over here. Whatever that thing is, I was going to map it into the map T would do. So that's how the map is defined. And now there's something you need to check here that we're not going to do. Need to check this is well defined. Okay, you have to make sure that this map actually makes sense. And again, you can just see the textbook. I just want to kind of give you the broad strokes here. So you can check that this map actually makes sense. And now we also want to define a map on these spaces. Okay, now this is kind of also why I didn't want to get into the proof, because this is one thing we haven't talked about in the text, in the course, okay? And this is like the only place there where we needed it. So this is called the orthogonal complement, right? And what it contains is all elements orthogonal to the given space. Okay, so what I mean by the orthogonal complement of the range T is it's all the vectors in V that when I use my inner product and I take something inside of the range of T and I do the inner product, I get 0. So I'm just taking those things that are orthogonal to everything inside of here. And over here, I'm doing everything that's orthogonal to everything over here. Okay, so we have to define some sort of map here. And details are being skipped here because it's a little complicated. Okay, so details are skipped. Okay, now, and as part of the reason I skipped it is because we didn't really talk about the orthogonal complement. We skipped over that section, and I think it's in chapter 3. Okay, so now there's one fact about orthogonal complements that we need, which we haven't proved, namely that if you have a vector space and you take a subspace and you take a complement of that subspace, V is going to be the direct sum of those two spaces. Okay, so you just believe me that this is true, and the consequence is that whenever we have a vector V, we can now write it as U plus W, with U in the range of the first subspace and W inside of the orthogonal complement of the subspace. Okay, and now I haven't told you how to do this map S2, but there is a way to define a map from this space to this space. Okay, so now you want to think about, we really want somehow a map from here to here. What we're trying to do is now have a map from this space to this space, and we want it to somehow take things in this red box and map it into somehow to inside of this red triangle. Now we have a map that does that, right, from the red box to the red triangle, but now we want to figure out, we want it to kind of also have a property that it takes everything in V to the things on this side as well. Okay, so we want to kind of extend our map to the whole vector space. And the way that we do that is now take any vector in our whole subspace. Okay, so think about it over here. We're taking a vector over here, and because of the direct sum, we can write it any vector as a piece in here plus a piece on the outside. Okay, and now we define our map by taking that vector U plus W, and we send it to, we break it up into its two parts, U plus W, and we send it so that the part that's in the range, like in the inside of the red box, gets sent to S1U, and the part that's not inside gets sent to wherever S2 would send it. Okay, because S2 is somehow telling me how to send things that are outside to things that are outside. Okay, now again, this is just a rough sketch, but hopefully you're getting the idea of what we're doing here with the map. Okay, so now we start putting together some of the pieces. Let's take a vector V that's in the range. So this is in the range of this operator, right? So it's saying that this particular element, right, is already inside of the red box. And now let's say, what does this map S do, right? So what we're defining, right? So we define an S that goes from here to here. So what happens to something inside of here? Well, something inside of there gets sent to the following. It gets sent to S1 composed with T star T V, right? Because this element is already in the range, so the W part is actually equal to 0 in this case, right? So maybe I'll write that as S2 times 0, or S2 evaluated at 0. Okay, so this part goes to 0, and now let's look at what this part is. Well, this part, right, it tells me that this sends this vector to TV, right? So this sends it over to TV. Okay, so what we have here is that this operator is the same as this operator right here. And just let me go through it one more time, because what we've done is saying that, okay, give me any vector V upstairs. Okay, now apply this operator. Okay, so you end up with this particular vector inside of the red box. Then apply this map S that we defined. It ends up where the map T would have sent the vector V. So both operators send the same vector to the same element over in here. So that means these two operators are the same. Okay, so this is just a rough sketch because what things have I skipped over? Well, there's lots of things I skipped over. Okay, we have to check that this map is well defined. We have to check that it's a linear map. I didn't even tell you how this map was defined, but then you also have to check that it's a linear map. Then you need to check that this guy here is a linear map. And then finally, we have this map S, but one thing we haven't checked is that it's also an isometry. So I wanted to kind of skip the details because otherwise it would have been an entire lecture to kind of go through all the steps of this proof. Okay, so but that's what the polar decomposition theorem is. And if you wanted to read the proof, hopefully this sketch will help you kind of keep the big picture in mind as you dive into the details. But what's important that we want to take away is that we could take an operator and write it as the composition of a positive operator and an isometry. So in the last part, I'll try to make things a little bit more concrete by looking at the matrix interpretation.